Let's start. Hello, everyone. Today we have 13th talk in the colloquium series, and it is the last one this year. First of all, I would like to acknowledge traditional owners of Australian land and pay my respects to the elders past and present. Today, I'm happy to present David Snoke, who is distinguished professor at the University of Pittsburgh. He is one of the leaders in semiconductor optics, including our physics of excitons and excitonic superfluids. He also known for the books and articles about connection between science and theology. David has a number of fellowships and awards. He's a fellow of American Physical Society, Alexander von Humboldt Fellow, and Cotter Scholar Award. Before we start, David has written me that he would be happy to interrupt it, and he encouraged questions. Okay, David, please feel to start, and we will enjoy the talk.
Well, thank you. And that's one nice thing about everybody doing Zoom is that we can cross the oceans and give talks all over the place. So I've been in your area, near Melbourne there, and enjoyed it a lot, and hope someday I'll make it back to Australia. So the talk here is going to be on one aspect of these polaritons, mostly in the gallium arsenide materials at low temperature. There's a whole other story of other things that we've been working on, which is moving this to room temperature, but that's a whole different story. So I want to make sure I especially acknowledge collaborators doing the growth of the samples. Lauren Pfeiffer and Ken West at Princeton have done a great job on these samples. And most of what I'm going to be talking about is the work of a couple graduate students, Shavik Mukherjee and Chi Yao are the present students working on that. Okay, so let's see here. All right, so I'm going to start at the beginning, just say a few words about Bose condensation, and then talk about polaritons. Then I'll go back sort of into the archives to talk about some the initial results that we had, and probably the last half to third of the talk will be on new results with long lifetime polaritons. I think most of you are familiar with the equilibrium distributions for the Bose-Einstein and the Fermi-Dirac distribution. So if we look specifically at the Bose-Einstein distribution, if we plot it this way, and this is actually going to be very similar to the way we think about the experiments, if we plot the number per state as a function of energy on a semilog plot, a Maxwell-Boltzmann distribution is just a straight line where the slope just gives the temperature. And then as we increase the density, what we see is the chemical potential approaches the ground state from below, and that pole that we had in the Bose-Einstein distribution gives us a sharper and sharper peak here. And one thing I would just point out is that even in a finite system where you don't have an infinite number of particles, you still are going to get this sharp peak. And so sometimes people will debate about, is a condensate possible in 2 dimensions and so on. And it turns out in general, for a 2-dimensional system and a finite system, it doesn't matter much. You're going to see a very sharp peak near the ground state, and that won't be infinitely sharp, but it'll be pretty sharp. Now, just how to think about condensates is just a little bit of philosophy, really about all condensates. When we get a large number of particles in a single quantum state, as we do for the Bose condensate, we can say it's essentially acting as a single wave. Now, one of the questions is, in these systems, since we're going to be pumping in light, what's the difference really between a condensate and just a coherent light beam? If we just look at the coherence, you might say that there's not that much. In fact, you could say I'm speaking to you right now using a coherent set of macroscopic occupied state of phonons, right? And so we can typically call those driven Bose condensates if you want, but it's basically a coherent state of bosons, but it's not spontaneous symmetry breaking. It's being driven by a force. In the case of a condensate, actually a really good analogy is imagine that you have a bell, and there's two ways to make it ring. You can hit it with a hammer, that would be a driven system, or you could just simply cool it down. And in this particular case for condensate, it's like a bell that you cool down, and below a critical temperature, it starts ringing spontaneously. And that's actually a really good analogy for a Bose condensate. So in the case of the Polariton condensates I'm going to talk about, actually both of these are possible. You can come in and with a laser just couple directly to the condensate and give it a phase, or you can cool down and see spontaneous coherence in the system as well. Okay, so I've already mentioned polaritons. So the way to orient yourself to what I'm talking about here is, I think it's easiest if you imagine starting with photons, clearly very good bosons. And now we're going to give them an effective mass. We're going to make them repel each other. And we're going to put them in some kind of a mirror box so that they have number conservation, so that they only weakly decay within the amount of time they need to thermalize. Well, if you do that, then you can immediately see that this system is going to have the same equations as atomic cold atom condensates, with just a couple little differences. On the one hand, you're going to have terms for weak generation and decay. You're going to be able to make the particles directly with an external source, namely a laser, which you couldn't do in the case of cold atoms, although you can have leakage of the atoms out of the system. And in some sense, you can say it's not just a bug, it's a feature. That light that's emitted from the sample is actually going to be what we're going to look at directly, so that we're going to be able to have direct measurement of the wave function by looking at the light that leaks out of the system. Okay, so let's orient ourselves toward these polaritons. The whole experiment basically is to have as I said, a mirror box where we have two mirrors created by DBR's distributed Bragg reflectors. And this whole thing is one monolithic device. So here it looks like we've got space, but that's actually just a transparent medium there. And so we now are going to embed quantum wells in the system. So we've got two resonances in the system. We've got a photon, which is confined to bounce between these two mirrors, and there's a confined mode for that. And that's illustrated, its dispersion is this red curve here. And this is as a function of the in-plane K vector, the in-plane momentum between these two mirrors. And then the excitons in these quantum wells, to a good approximation, we can just treat that as a constant energy. Now, those are going to couple to each other because a photon can be absorbed by a quantum well, turn into an exciton, and then the exciton can emit a photon. So there's going to be a coupling between these two. So when we turn on that coupling, just before I talk about that, there's going to be an effective mass for the photon just due to that curvature. Okay, that's going to come back in a minute. Okay, when we turn on the coupling, we get now a mixing or an anti-crossing of these two states. And the eigenstates of the system now are the upper polariton, the lower polariton. So we started with photons and excitons being distinguishable. But now when we go into the strong coupling limit, now we can't really talk about those separately. We're going to talk about eigenstates which are mixed superpositions of the two. And this is kind of important because sometimes I'll get people asking me, well, what happens if you stick a photon into the system? Essentially, in this system, the photon is already accounted for in the polariton effect. So there's no additional photons around. The eigenstates of the system are properly this lower polariton and the upper polariton, and there's not some additional photon states around somehow. So now our attention we're going to focus on primarily is going to be on this lower polariton. This still has that effective mass, which you can view as just sort of fitting this to a parabola, which was picked up from the effective mass of the photons in the cavity. But now, because they've got this excitonic part, they now have this very strong repulsion of each other because two excitons repel each other. So one way of thinking about the system is to think that we've taken photons and we've given them a very, very large chi3. We've given them a very strong repulsive interaction from each other. And that's controlled by the fraction, which is the exciton in the superposition. So now we've got all the elements that I talked about. We've got an effective mass, just due to the curvature of this here. We've got interactions that repel them, and we've got mirrors that keep them in for a while. In general, one of the reasons why we want to look at these polaritons is because of this general consideration here, that the mass is extremely light. When we look at the mass of this curvature, the effective mass is about 10 to the minus 4 electron masses. So if you think about that, an electron is already 1,800 times less than a nucleon, and a typical atom has, maybe 100 nucleons. So we're talking about something that's extremely light. Now, if you just do unit analysis, you can say that the quantum effects become important when the distance between the particles is comparable to their de Broglie wavelength. So we can just rearrange this, and we can write the distance between the particles in terms of their density and the dimensionality of the system, which here is going to be 2 for a two-dimensional system. And we can write the de Broglie wavelength in terms of the temperature and just rearrange, and we find that the critical temperature for quantum effects goes inversely with the mass. So when we have this very light mass, that pushes the TC up enormously higher. So the experiments I'm going to talk to you about are typically done at 10 to 20 Kelvin. There are people who have reported in systems I'm not going to talk about condensates at room temperature. Actually, it's really not heroic temperatures and all of this because of these extremely light masses. So just a little background in how we control these then. So these are, like I said, effectively photons with mass. They don't have a net charge. So we have to think about how we can move them around and control them, put them in traps and so on. And in general, since they have an exciton part and a photon part, we can control either one. So in the exciton side, we can shift the exciton energy using strains, and I'll talk about that in a minute. We can also use other carriers to push off of them. And we can also directly use a laser. There's a solid state analog to the AC Stark effect, where you can simply tune a laser below the band gap and shift the energy of these states. I'm not going to talk about that in any depth. We can also play around with the photons by changing the cavity width or changing the cavity Q, and I'll talk a little bit about those methods as well. So we've got a whole palette of different things that we can do. So I'll just talk about a few of these.
Can I interrupt you?
Sure.
A question. So what limits the smallness of the mass? Is it possible to make, it's probably size of the cavity, is it possible to make mass even 1 or 2 orders of magnitude smaller to increase the critical temperature?
The effective mass is controlled by that the length of the cavity, the distance of the cavity, and so these are microcavities that are of the order of microns in spacing. One of the things that's crucial for this effect is to have a resonance between the two energies, the exciton energy and the photon energy. So if you're going to push that mass up higher, you're talking about pushing the ground state energy up higher, which means then you've got to find a medium that is in the ultraviolet or something like that. So you might get another factor of 2 to 10 orders of magnitude lighter would be, I think, pretty hard. Because you're talking about a very, very thin cavity then with a very high gap.
Okay, thank you.
Yeah. So this is a method we actually developed almost 20 years ago now, which is using strain to bend our sample. So if you look at this picture here, we can clamp the sample, poke it with a pin, and actually flex it. And when you flex it, you think about the ping coming from the top. On the top, you're going to have hydrostatic compression. On the bottom, you're actually stretching the material. And so as you stretch it, you increase the volume of the unit cells, and that will actually drop the energy, drop the band gap of the material. And so this is just a calculation of those strains. And the theory here, the red curve, is the calculated shift in the band gap just due to these deformation potentials, which are well known in gallium arsenide. And then the blue is data. So this is not polaritons. This is just a pure exciton and a quantum one. You see that we get a very nice dimple or a harmonic trap to confine these things. So I'll come back and talk about this in a few slides, how we can use this to move these things around. Now, this is actually a very important slide for how we actually do the experiments. What you see here is a plot of the upper and lower polariton as we go across the wafer. So these wafers, as I said, are grown as monolithic wafers and shipped to us, and then we cut them up. And there's actually a thickness variation of the layers as you go across the wafer. Now, what that does is it means that the mirror is changing the effective energy of that photon. And so we have a very strong dependence of the photon energy as we go across the sample. The exciton is nearly constant. You can see it's not perfectly constant, but it's fairly flat compared to the photon. So there's going to be an anti-crossing region, which is just now in real space, the same anti-crossing that I showed you before in K-space. And this is because we have a shift of the photon energy in space. Now, there's a couple things that follow from this. One is that this is just a gradient of energy for this lower polariton here. So if I create a blob of polaritons right at this point, they're going to feel an energy gradient, i.e. a force, to cause them to move in this direction. So we will typically talk about the uphill and downhill in the crystal. And what we mean is higher polariton energy and lower polariton energy on this lower branch. And so we can use that to put a force on them. Now, a separate thing that happens is, if you remember, the polaritons are partly excitonic, partly photonic. So out in this region here, they're mostly excitonic. Over here, they're mostly photonic. And in this resonant region, they're about 50-50. What that means is if we pick different places on the sample, we can actually control the exciton fraction. So we can pick how much exciton we want. And that has the important effect of allowing us to tune the interactions. If we go over here, they're going to be strongly interacting. If we go over here, they're going to be mostly like pure photons and very weakly interacting. So it's not the same as a Feshbach resonance, but it's sort of analogous in that we can tune these interactions over a range from nearly non-interacting to reasonably strongly interacting. What we can't do is switch the sign of that interaction. These are pretty much always repulsive for the experiments I'm going to talk about. Lastly, one of the things that we can do is simply make a lot of excitons. So if you remember the curves I showed for this lower polariton, there's sort of this dimple in K-space here with a very light effective mass, and that's our active region of our polaritons. But if I keep following this branch up, there's going to be it's going to turn into the excitons, and the excitons have a much heavier mass. That's of the order of an electron mass, which is about 3 to 4 orders of magnitude higher than the polariton mass. So if we populate this upper branch here of excitons, they're going to be very slow and very heavy as seen by the polaritons. So it's like putting a bunch of bowling balls in the system, and then the polaritons are like ping pong balls bouncing off of them. So we can just make a blob of excitons, and then that becomes a barrier that the polaritons will bounce off of. So here's an experiment not done by our group, done by Baumberg's group a few years ago, where they used this to make an optical transistor. So they tuned one laser to create a blob of polaritons, but in the same spot, they created a bunch of excitons. And so the excitons are just sort of shedding polaritons, turning into polaritons. And because of the wedge in the cavity, these polaritons then move downhill and will move out this end of the sample. However, if they come in with a second laser, they can create another blob of excitons, and that creates a barrier to block these polaritons from moving off of that side, and they get stopped there. So that's one configuration, and I'll show you experiments in which we did something very similar as well. So there's a bunch of other methods I'm not going to talk about. This basically gives us now a palette of techniques to make our samples. And so the initial experiments, which are now, let me see, it's like 2006, 2007. So that's already more than a decade ago. Were done with fairly short lifetime samples. The photons leaked out of the mirrors fairly quickly, but we can still see a lot of the canonical effects. So remember this power law that I gave you, which is generic. Typically, when people think about condensates, they think about sitting at fixed density and dropping down below a TC. In the experiments that I'm going to talk about, we typically are going to stabilize the temperature, and then we're just going to turn up the pump to put more and more particles in. So we're going to cross our phase boundary, the same phase boundary, we're going to go above a critical density. So you'll hear me talking about a critical density that we go above in order to get into our superfluid region. When we do this in a trap, that means that we're going to have a condensation in the ground state of the trap, which in this case is going to be a localized in the center of the trap. All right, so let's look at some actual data here then. This is, as I said, old data in a harmonic trap. At low density, you see a big thermal cloud just sort of filling up this trap in some kind of quasi-equilibrium with steady state with pumping. And now as we turn up the laser, what we see is that instead of the pressure causing it to expand outward, as you might expect with a normal hot gas, it actually condenses inward. It actually moves inward because it's now approaching the ground state of the trap. And as we move through that transition, then we have the condensate sitting mostly in this ground state of this trap here. Now this is in real space. We can also then switch to momentum space. And this is a really nice feature of these experiments. Essentially, if you think of our system as a two-dimensional system, the polaritons are moving between two mirrors in a plane. Snell's law says that the momentum of the polariton in the plane has to be preserved if it turns into a photon leaking out of the cavity. And so that means there's going to be a one-to-one correspondence between the momentum of the polariton and the external photon, which is emitted. So that means we can simply angle resolve. And as we angle resolve, we'll immediately get the momentum distribution of the particles as we look at that. And so we simply look at the far field Fourier emission of the light emitted from this. And basically, you just switch with a flipper mirror. You can go back and forth between real space imaging and momentum space imaging by just doing the Fourier transform as you look in the far field. So this is now momentum space data, where you see, again, at low power, a broad thermal distribution. And this curvature is, again, just that effective mass of the lower polariton. And now as we move through the transition, increasing the power, we see that that sharpens up into a peak in momentum space. So there's actually two types of sharpness that happen here. In momentum space, we see that we've got a peak near k equals 0. And we also see, if I take a slice in the vertical direction, that now I have a narrow energy distribution. This is energy versus momentum. That corresponds to a coherence. So this is something familiar to a lot of laser people. When you have coherence in the system, that corresponds to line narrowing. So we have line narrowing as an evidence of coherence in the system as well. Now, if we just plot the same data in different ways, we see that we have this peak growing up in the ground state as you would expect. However, these distributions are actually non-thermal. If you were to try to fit an equilibrium Bose-Einstein distribution to these, you would find that you didn't get a good fit that this tail would actually be too hot for the condensate fraction that you actually see. And that's directly related to the fact that these in these early experiments, the lifetime was just a few picoseconds, and that's comparable to the amount of time it takes for them to thermalize. And so you see a lot of the canonical condensate behavior, but you don't actually get a true equilibrium distribution. So the next thing to do, of course, then is to try to go to longer lifetime to see true equilibrium. So starting about 8 years ago or so, it's been actually several years now, we moved to making long lifetime samples with much higher Q. Now, in principle, to get longer lifetime, it sounds very simple. You just make the Q of the cavity better. You can just think of Q of a cavity effectively gives you the number of bounces that a photon makes between the two mirrors before it leaks out. And so if we increase the Q, we've increased the lifetime of the particles in the system. To increase the Q, we can simply add more layers to our DBR stacks. You know, that all sounds very good, but since these things are grown by MBE, it turns out actually to be really a heroic MBE growth, about 30 to 40 hours of MBE growth, during which the whole thing has to stay stable. And that's a really remarkable accomplishment by the Pfeiffer group to keep things stable for that long, so that we have monolayer smoothness in a very, very thick structure. Indeed, we then now see that the lifetime of our particles goes up to now over 200 picoseconds, typically. So I'm going to show you a cute experiment that shows you the how we know this long lifetime of these particles. So this is now going back to the same diagram I showed you before, where I said that there's a one-to-one mapping between the external photon and the polariton in the cavity. Well, just time reversal says actually it works both ways, right? So if I inject with a laser resonantly, I can directly create polaritons with a momentum chosen by the angle of the external laser. And so this is just resonant injection at a particular momentum. So we can use this for a very cute experiment with these long lifetime samples. Here's, again, we have a wedge in the cavity. It's got a gradient of energy. And so we can represent that in a cartoon as just a inclined plane, right? There's a gradient potential energy for the ground state of the particles. Well, we have particles with an effective mass, and we can inject them with a well-defined momentum. And so we're going to do that in this experiment, inject a laser here, watch them move along here, and then image them over here, and then we're going to time resolve to see what happens. So a little bit of a thought experiment, predict what happens. This is freshman physics, right? We've got particles with mass being shot uphill. They're going to trade off kinetic energy for potential energy until they lose all their kinetic energy. Then they're going to turn around and go back the other way. So that's what we have here. This is data showing these particles shot in one direction, turning around and going back the other way. And so we learned a bunch of different things from this. If we simply map the intensity of this as a function of time, we get a direct readout of our lifetime, in this case about 200 picoseconds, and that's tunable based on the photon fraction. We also can get a measure of the quality of the sample by seeing how far they go. You can see here they've actually gone millimeters. So we're shooting these polaritons millimeters through the sample. In order for that to be the case, they have to have very, very low disorder. They can't be scattering too much, or they wouldn't stay in a nice wave packet moving like this. So it's kind of cute just to think about what's going on here. We essentially have dressed our photons, given them this effective mass, given this potential energy gradient. And so now it's just kinetics. But if you think about the photons, you're literally saying there's no interface to reflect off of. The photons are just moving in, slowing down, turning around, and going back the other way again. So it's interface-free reflection. Or if you will, it's the slowest slow light in the world, right? Because at some point they actually reach zero group velocity and turn around and go back the other way. And so this is actually doesn't require them to be a condensate at all. It just requires them to have low scattering so that they stay in a nice wave packet that we injected. All right, well, what can we do with now that we have the system with these nice long lifetime samples? This is an experiment we did.
David, could I interrupt you?
Sure, absolutely.
What happens if we add disorder? Is it become noisy? Could you see each collision?
Yeah, you would expect that, and then they just scatter out. So here they're basically moving ballistically as a wave packet, and you can see if you were to take slices through this in the vertical direction, you would see that it's spreading out, right? So that a slice here is wider than a slice here. So that's basically diffusion. So they're moving, say, in the X direction, but they're smearing out in the Y direction, and that is basically just diffusion. All right. So if there's a lot of scattering, they're going to diffuse outward, and you won't get nice trajectories like this. You'll just see a smear as they scatter in all different directions. So this requires them to have ballistic motion without too much scattering.
It looks like that when it returns the right part of the curve, this uncertainty in Y direction, it becomes smaller. So
that's actually just a coloration effect. It's because of our color scale, because they're also dropping in intensity.
Oh,
right?
I
So
see.
you see they're dropping intensity. So this is not normalized, right? So that there is a lot of them here, and then they're actually at late times it's just dropping below this threshold of the blue. But if you actually did take slices, you would see it's spreading out.
Okay,
the other direction.
I see it. Thank you.
So this is a nice experiment done in collaboration with Keith Nelson's group at MIT. We're now making an optical trap. So the laser that's exciting the system is now focused in a ring on the sample. And a lot of people like this configuration. It makes a nice, well-defined trap. The polaritons that are created now occupy this, which has basically hard walls. And now, if you make it cold enough and dense enough, you can see as you turn up the power that you have just really nice fits to the Bose-Einstein distribution. So as I said before, we didn't get good fits to the Bose-Einstein. Now, actually, under proper circumstances, you can get it to be nicely thermalized and held in this trap this way. So we can go on and do some other cute things. This is an experiment that a former student of mine did, Gongxin Liu, who actually has moved into doing cold atom condensates. No, that's not true. He did some collaborations, but he's not doing that now. This is now a system in which we have several things going on at once. So we've got the strain effect, which gives this dimple, which gives us a harmonic potential that I was telling you about. There's also a net gradient from one side to the other. That's due to the wedge in the cavity that I was telling you about. And so we get sort of an asymmetric minimum. And in this data here, we've defocused the laser to light up the whole thing so we can just measure the potential energy profile. Now we're going to focus down the laser just to a single spot. And you can see it's tightly focused. That's creating a wall because, as I said, the excitons created by that laser will basically sit where you put them, and that forms a new barrier. Now, the same population of excitons is now going to shed polaritons. Some of them are going to turn into polaritons, and some of them get stuck in this little nook here, right? So we've got the overall potential energy profile, and we've got this wall. But some of them will get stuck here, and some of them will go around the barrier and flow to the bottom of the trap and get stuck here and make a nice condensate down here at the bottom of the trap. So we can have sort of two spatially separated condensates just by putting a barrier here. But now the nice thing is this laser we can move around, just a fence post that we can focus anywhere. So we now have moved it to the center of the trap. And we've got a post sitting here. We've got a harmonic potential. And so that is sometimes called a Mexican hat potential or wine bottle potential. We've got a two-dimensional system with a post in the middle and a harmonic potential on the outsides. And now we can turn up the power and make a nice condensate. And this is now just doing XY imaging. So we're just looking at an image of this ring. And you see that you have a ring going all the way around. It has a variation in density. But what actually I'll show you is that it's actually going to be a single energy state in which it reaches a common energy by having slightly more density in some regions to cancel out where there's a little bit of disorder, making the potential energy a little bit lower in the trap. So here is energy versus position, where this is below the threshold. You see here we've got this blob of excitons being created, and we have the polaritons are broad and thermal. And then when we go above the condensate threshold, you see we just have a perfectly nice condensate, monoenergetic all the way around the ring at this point. So now we can do some cute stuff. We can do some interferometry and take that image of that ring and send it through two legs of a Michelson. So one of the images will go one way and come out, and the other will be flipped left, right, and come out. So now we're going to interfere the ring with this mirror image, and we're going to look at the coherence measured by doing that. And when we do that, we get really nice interference fringes. So along this vertical slice here, position 0, that corresponds to the light from the center of the ring, from one slice interfering with itself. But on the sides, this corresponds with light from one side of the ring interfering with light from the other side of the ring. And so we're showing that it's one single coherent entity all the way around the ring. Now, this is already a cute effect, but you can actually study this quantitatively. And so one thing that we just noticed right off the bat is if you actually count the number of fringes going around this ring, if you count across the top, you get one number. If you count across the bottom, you get a different number, and those differ by 1. So there's actually a phase defect. This is not just straight fringes. There has to be some kind of phase defect in the system. So what you can do, and here you can do it another times, another shot. Sometimes it comes out the other way. You get one more fringe on the bottom than you do on the top. So a nice way to analyze this is actually to do what's called a phase map. So what you do with the phase map is you Fourier transform your real space image. And then that's going to give you a peak in K-space that corresponds to that fringe spacing. Then you just erase those fringes, the peak that corresponds to the fringe. And then you Fourier transform back to real space again. And you get now just the phase that corresponds to the phase winding without the fringe spacing. And you see indeed that what we have is a phase gradient winding around. In the case here, we have it winding clockwise. Here we have it winding counterclockwise. And then sometimes we've got no phase winding. Now, let me remind you of a little bit of condensate physics here. And a condensate, the phase gradient corresponds to the current. So when we see this phase winding, that actually is corresponding to a rotation of the condensate in this ring. Now, in a standard condensate, if I do any closed loop and I go back to where I started from, basically my phase has to wind by 2 pi to get back where it started from. And this is what gives the canonical effects of flux quantization or field quantization in superconductors. The fact that you have to have quantized amounts of phase winding around any given loop. Now there's an extra complication in the case of these polaritons. And this is something I haven't really stressed yet. This is actually a spinor condensate. It's actually 2 degenerate states. If you think about photons, they've got 2 polarization states, which you can think of either as left and right circular or horizontal and linear. And so we have an extra degree of freedom in this polariton condensate, which is there's a polarization angle, which we can talk about as well. So there's another way to solve the boundary conditions. If I go around the ring, instead of having a 2 pi phase winding, I can have a pi phase winding and then also a pi polarization rotation. And the two together will give me a net of 2 pi and allow me to satisfy my boundary conditions. This has actually been predicted a long time ago. in regular low temperature physics, and it's called a half quantum vortex. And so we can actually show that we have that state. So if we look at these phase maps carefully, we see that this phase winding is pi, not 2 pi. Seems odd, but then we can also directly measure the polarization. And when we do that, we see, if you notice here, the polarization here on one side, this is theory and experiment, is linear this way. It winds by 90 degrees, so it's polarized perpendicular over here, and it winds by another 90 degrees by the time it gets back. So that's a pi polarization winding added to a pi current, which gives us a 2 pi net, which allows us to satisfy our boundary conditions. And so this is actual data showing a linear polarization phase winding. And then interestingly, there's also a precession of the circular polarization degree of freedom, which is accounted for by, again, you can just satisfy that in this state here, worked out by Andrew Daly. And what you see is it's a single quantum state, one energy, but it has a precession from up spin to down spin, and also a linear degree of freedom, which is winding by pi as it goes around the circle. So it's a very unique state of matter. And we can get it to circulate either direction. We can get it to circulate to the left or to the right. Okay, a lot more that I could talk about with that, but I want to kind of jump to the present a little bit more. So is there a question on that before I move on? Sure.
Yes. So to get 1/2, you have, for instance, two options. You could, so you have rotation inside the prefecture and rotation inside the spinner.
Yeah.
So you could have prefecture.
There are 4 solutions, right? So you can have pi winding of the phase this way or that way, and you can also have your rotation this way or the other way. So there's 4 possible ways to solve the boundary conditions. And so what happens, it's a little bit of a detail, the polarization degree of freedom in our samples is pinned. It's not spontaneously broken, but the phase gradient, the direction of the current flow is spontaneously broken. And so sometimes it's flowing clockwise and sometimes it's flowing counterclockwise. It's a very interesting set of conditions.
So you mean that all four possible solutions can be realized in experiments depending on some random prehistory?
Yeah, well, okay, so the flow is spontaneous symmetry breaking, and then the polarization has to do with actually the details of the cavity itself. Okay, there's actually the crystal favors one polarization over another at different points in the structure. So that's actually printed in from the 100 symmetry of the crystal, which is a detail that I could come back to maybe.
Okay, thank you.
Mm-hmm. Other questions?
Any other questions? It's just woeful.
Okay, so just a couple more experiments bringing us up to the present here. So the ring experiment I showed you was nice in a lot of ways, but one drawback of it was that the potential energy profile was a function of the pump, because that center laser pump, the harder you pump, the higher that barrier is. So we moved to etching down our structures to make just plain rings in this case. And you can see that we make these thin enough that now there's quantum confinement in the transverse direction. So this is a slice in the radial direction. And you can see that we have quantum confinement of these states. Effectively, what's going on here is that we have both a small structure and we have strains at the edges. And the strains at the edges, just from what I talked about before, give us a shift to the band gap, and in this case give us something like a harmonic potential as seen in the radial direction. So they're free to flow around the ring in one dimension here, and then they can jump or hop from one state to another in the radial direction. Okay, so here's another thought experiment, sort of a challenge to all of you to predict what's going to happen. I've already given you the one with the flowing uphill, right? So here's another semi-classical Hamiltonian. We have a one-dimensional motion confined to a ring, all right? So that's like a rigid rotator. And then we have a gradient, which gives us gravity, okay? So we have a rigid pendulum. And we're going to create the polaritons at the top of this ring and then watch them flow freely. Okay, so what do you expect to happen? All right, you don't have to commit yourself publicly here, but you know what's going to happen, right? You're going to see oscillations. All right, so it's basically a rigid oscillator. So again, because these things can ballistically move, they're going to go around the ring and oscillate. And so this is just looking at different points on the ring at different points in time and seeing that we have this oscillation. Now, this is maybe easier to visualize with a movie. So my student Shalvik Mukherjee spent some time doing a movie. And so I'm going to show this once quickly, and then I'll show it to you again a little more slowly. We're creating it. The ring is here. The high energy point is here. The low energy point is down here. And so several things are going to happen. One is the first thing that's going to happen, they're going to ballistically stream out very quickly and fill the entire ring. So we'll have a connected condensate filling the whole ring. Then the density is going to drop, and eventually it will fall to the bottom and it will slosh back and forth at the bottom of this ring. And then finally that will be damped out, and we'll just have a single condensate in a Gaussian profile sitting in the bottom of this trap at all later times. Okay, so is my movie going to work? Oh my, you know what?
You might need to change to the regular pointer instead of the laser pointer.
Okay, that's good to know. Let's see. That automatic here? Ah, wow, that's really nice to know. All right. Okay, here we go. All right, did you catch all that? All right. This is using a street camera to measure this in time resolution. Okay, so here we go. I've stopped it here. You can see we injected it. It flowed throughout this whole ring. All right, so now we've got a nice ring. And there's so much I could talk about this. I don't have time, but there's actually very similar to something I showed you before, this polarization precession going on around this ring. All right. All right, so you can see it around the ring. All right, and there, did you see that sloshing? I'll move it back a little bit here. Okay, look at the bottom. Okay, you see that sloshing? And then at late time, it just sits there and relaxes as a Gaussian. So there's a lot of different things going on. I can plot this in a different way. This is now just looking at the bottom of the ring at one point on the ring and resolving an energy. And you see, again, there's this sort of non-equilibrium sloshing. And then at late times, we finally have the appearance of what we call a true condensate, which is monoenergetic, which is then decaying away at very late times. Okay, now one of the things that was happening here, and you can see in this picture, is there's dissipation, right? So it's maybe surprising to you, to some people, that we have a condensate. I'm calling condensate. It's coherent. If we were to do interference, we would see fringes, and yet there's dissipation going on. And sometimes people will say naive things like a condensate has no dissipation or it has no drag. And that's actually not quite right. What you can say is a condensate does not have transverse drag, but it still feels body forces. And so if you have a bucket of condensate and you drop it, it's still going to fall down. It's not going to hover. All right. And so a body force acting on a condensate works perfectly well. On the other hand, if you try to use the sides of the bucket to slide past the condensate will not feel friction with those walls and it'll stay where it is. So the polariton condensate here will have superflow around the ring. On the other hand, as seen by these phase coherence, on the other hand, it has a body force of interaction with the excited particles. And there's also the body force of this so-called effective gravity due to the wedge of the cavity. So the next series of experiments, and I'm going to skip this and come back to this. The next series of experiments is a direct measurement of showing the interaction of the particles.
David, could I interrupt you? Could you show this ring again?
Which do you want to see?
Yes, the ring. If if we look at like at the pendulum, if it is start on the top, yes. If
it's not trapped, it's injected at the top. It's not trapped there. So it's injected here, and then it shoots out ballistically until it fills the whole ring.
Could I think it's like a pendulum where the gravity is directed to the bottom?
Yeah, so there's a gradient of energy. So the potential energy is higher here than it is down here. And that's due to this wedge in the cavity that I was showing you before.
Yeah. So the question is, if you shake this potential, is it possible to realize this Kapitsa pendulum where you have metastable state on the top?
Yeah, it is in principle, except that the time scales for shaking are difficult to work out, because even if you were to come in with, say, like a sound wave, that is still going to be something on the order of like kilohertz to megahertz. And these light times are like 200 picoseconds. So in principle, yes, but we don't know of a way to shake it on picosecond timescales. So the natural frequency of this is about 20 picoseconds for the oscillation time. So you need to oscillate it on that kind of time scale. It's not inconceivable that you come up with like an optical modulated signal that would modulate the potential somehow that way, but we haven't figured out a way to do that very well yet.
Okay, thank you.
Mm-hmm. Okay, so last experiment, and then I'm going to be out of time. Now we're going to create a wire. Instead of a ring, we just have a straight wire, but it's similar in that there's a quantum confinement in this transverse direction, and there's one-dimensional flow in this direction. So now we're going to create it at one end and just watch it flowing in a straight line. And the reason why we're doing this geometry is because we're actually going to run electric current through the same structure. So we now have contacts. So we've exposed the quantum wells here. So we've etched away the mirrors here, but we've exposed the quantum, so we can directly inject current and extract it from that side. So we can do simultaneous measurement of current and watch what's going on to the condensate. So the experiment is going to be, we're going to inject a condensate, watch it flow. And you can see here, when this is now for 0 volts, this potential energy profile is due to the laser spot. Remember I said the laser spot creates excitons. So there's like a blob of excitons that makes a hill there. Then far away from that, the wire is basically flat, slightly downhill. And you can see now a condensate appearing in this long flat part of the wire, about 200 microns long. Okay, so now we get, again, nice monoenergetic condensate extending throughout this wire. Okay, now we're going to turn on the electric field. All right, and we're going to see, now we're resolving in K-space. So if we look at this long condensate, this is in real space, but if we resolve it in K-space, we see we have a peak not at K equals 0 because it's a flowing condensate. They're injected at one end, they're flowing in one direction, as they die, there's going to be a net steady state flow in one direction. So with no current applied, that's this middle one, we have just sort of a peak. And actually, we have a little bit of a bounce back. This is when they actually hit the opposite end of the wire. And there's some of them that are actually backflowing, but not too many of them. And now we can turn the current on, and we see we actually are shifting the momentum of the condensate by applying our electric field. Now, it's a little bit surprising at first because I told you before these particles are neutral. They don't have any charge. And so you would think, well, how can electric current have an effect on these polaritons? Well, in a sort of cartoon Feynman diagram, we realize that the polariton you can think of as a photon turning into an electron hole pair, which turns back into a photon, which turns back into an electron hole pair, and so on and so forth. So it's spending part of its time as an electron hole pair. While it's an electron hole pair, another electron can come along and bounce off of it with a Coulomb interaction and impart momentum to it. Another way to think about it is just that, remember, the polariton has an exciton part. It's partly excitonic, and electrons and excitons can exchange momentum. And so if I have a flowing electric cloud, that will bounce off of the excitons in this polariton and impart momentum to it. And so you can see here, this is just a plot of the curves above. You can see that you're actually imparting momentum directly to the condensate, even though, again, this is a coherent condensate in a monoenergetic or nearly monoenergetic state. Now, to explain this, there's some very nice theory inspired by Ashton Bradley. When I was over in your part of the world in 2020, I spent the first few weeks with Ashton Bradley over in New Zealand, and he worked out this theory of drag on a condensate for the case of cold atoms. And the idea is that you can sort of think of it as two populations, the condensate part and the thermal cloud. And in our case, we have a very definite thermal cloud of electrons around, as well as neutral excitons. What Ashton showed is that when you do that, you actually have a real potential energy. So if I go back to the Gross-Pedievsky equation, which I skipped before, typically you'll treat these polaritons with what's called a driven dissipative Gross-Pedievsky, where you have a typical Gross-Pedievsky equation, then you have terms for decay and terms for generation. And the decay is an imaginary term, you're just losing particles. But in the case of drag, you actually have an additional term, which is a real potential energy. And you can think of it like a soft pillow. If I'm sitting on a pillow and I push to one side, there's going to be a push back of that pillow that's a function of how much I'm pushing on it. And so you'll actually have a renormalization of the potential energy profile due to the current of the electrons. And so since this isn't a theory talk, I'll just give you the results here. This is the experiment showing both the energy shift of the condensate as a function of different currents. And you can see what's going on. At zero momentum, you have sort of this intrinsic flow. And here they're jumping between two different transfer states. If I'm trying to push them in the same direction, I don't get much of a push because I'm sort of chasing them. If I push oppositely to their flow, I'm giving them a kick up because I'm having a lot of scattering pushing oppositely to them. And there's a much bigger energy shift up. And that's seen in the theory. Here you can see that between the positive push and zero, there's not much energy shift. But if I push oppositely to them, I see a push up in energy, just due to the fact that I'm now ramming electrons against their motion and giving them a much bigger momentum kick. And here you can just see theory versus experiment for the K-space shift that we saw experimentally. Okay, so I'm pretty much out of time, I think. So I'll just finish up here. Lots of nice features now that we can see with these long lifetime polaritons. I haven't talked at all about the experiments done by someone just down the road from you in Elena Ostrowskova's group at the ANU. You might want to have her in to give a second talk at some point if you haven't already, to talk about some of the very nice things where she's done direct observation of the Bogolubov branches and things like that. As I showed, we have lots of ways to control these things to make them flow in rings and wires and things like that. Perhaps surprising, perhaps not, depending on your point of view. You can see a direct drag of an incoherent bath acting on a condensate. And just for future, we can talk about now with these etched wires that we can make, we can talk about polaritronics, where we send condensates through wires, have junctions, switch them from one side to the other, and so on and so forth. So before I forget, Pittsburgh is a wonderful place. I'm in recruitment mode. If anyone's looking to do a postdoc, or for that matter, to be in graduate school. I'm also actually trying to hire a staff person, a permanent staff person. So anybody who wants to come to Pittsburgh, it's beautiful, green. We have winter here with actual snow. If anyone listening or knows somebody who is looking to maybe come and work on these things, let me know. And this is my some of my group members. I said Shalvik Mukherjee did a large part of what we're talking about, and Jonathan Bummeridge and David Myers, the last part where I talked about the wires was mostly his work as well. All right, so I'll finish with that. Thank you.
Thank you for great talk, very beautiful physics. Do we have any questions? We have a couple. Mira, please go ahead.
Oh, hi. Yeah. Hi. Hi, David.
Hi there.
Hi, nice talk. Yeah, actually, I think maybe I have a very general question, actually. I guess a lot of the physics you talked about involved linear excitons, mobile excitons. How, if at all, would the physics change if you had, say, these localized excitons, or say Frenkel-like excitons in the polariton?
Yeah, to first order, not much, actually. This is actually stuff that Jonathan Keeling and Peter Littlewood worked out way back in, I don't know, 10 years ago or more. If you literally took the excitons and nailed them down so they couldn't move at all, it wouldn't change the effective mass or the motion of the polaritons hardly at all. Because the mass of the excitons, even for these Wannier excitons, is so much heavier than the effective mass of the polariton. Effectively, the motion of the polariton is entirely in the photonic part. And so you just think of it as bouncing down between these mirrors, and every now and then it gets absorbed, turns into an exciton, spends some time there, and then turns back into a photon. Now, of course, that's not really what's going on because it's a quantum superposition. And so it's really kind of doing both at the same time, but you can sort of visualize it as the motion is entirely in the photonic part. And so that effective mass comes almost entirely from the part. Now, the caveat I have is the materials that people have looked at to do the room temperature polaritons with very large binding energy typically have much stronger disorder. And so that disorder does play an enormous role in reducing the mobility of the polaritons. That's really not intrinsic. That's a detail of the particular materials that people are using, but no one's found a way. I mean, so, you know, these gallium arsenide is low temperature, but I mean, we have millimeter diffusion lengths, right? You know, like if you get 10 microns, if you get a micron in these high temperature systems, you think you're doing really well. So long range diffusion is still an issue with these high room temperature ones. So most of the room temperature condensate results. Now, the perovskites is an exception. I think perovskites, they actually see pretty decent, maybe 10 or 20 micron diffusion lengths, if I remember right. Most of the other ones, the 2D materials, the organics, the mobility is pretty low. Okay, but I'm sorry, just to quickly follow up. But what about, for instance, in terms of like scattering, like scattering with electrons and things like that? That presumably would be modified in that case. Like in the drag effect we're talking about there. For instance, yeah. Yeah, so essentially their scattering is going to be sort of sum of all of the above, right? So they're going to scatter off phonons, excitons, disorder, and moving electrons. So if the disorder is too great, you might have a very high resistance, which would mean your electrons are not moving very fast, and then you couldn't impart much momentum. So I mean, the actual electrical resistance matters here, because you have to have a decent flow of these actual electrons. Thanks. Mm-hmm.
Okay, we have a question from Eli Estresha.
Hi, Eli.
Wait, sorry.
I think you were in one of my. I think you were in one of my pictures, actually.
Yeah, I was on the second last slide.
Where was that here?
During my visit, yeah, the second last slide. Second to the last slide, yeah. I have a question about the drug experiment. So you basically designed it to have a flowing condensate, right? I'm just curious, and probably a very naive question. What if the condensate is stationary? Will you still see a very obvious shift between left and right?
In principle, it's a harder experiment to do because if you illuminate with the laser everywhere, then you're creating excitons everywhere. And they are going to really interfere with everything. So part of what we're trying to do is to have like the excitons far away from the region where we're looking. Now, you still get some excitons everywhere, as you know, but you know, if you have the excitons illuminating the whole wire, you have this big potential energy shift just due to the excitons, and so that becomes a thing. But there's no, in principle, reason why you couldn't. As a matter of fact, actually. Unfortunately, I don't think I have. I'm going to go back to screen sharing here. If I can figure out how. Let's see here. Go back to screen share. Okay. Let's see. Yeah, there's Eli.
Yeah, how's that?
Yeah. Okay, yeah, if I go back to looking at these, not sure I have super good, oh, maybe here. Yeah, okay, look here, and now maybe I'll go full screen. If you look here, you actually see localized condensates trapped in local minima here, okay? So now there's actually no flow. Okay, because what's happened, and you're familiar with this effect, there's sort of self-trapping of these things because they can dig a hole in the exciton cloud and self-trap, and you get these localized condensates. So in that case, it's very hard to pick up any K-space movement because there's walls right beside them. Okay, what you do see though is an energy shift. When you turn on the current, these things shift up for the current in both directions, right? Because you're kicking it to the left or the right. Either way, you're pushing it up a wall, all right? And so you see in these localized traps, it actually is moving up no matter which way the current goes, because they're being, think of it as like you're sitting in a trap and somebody's pushing this way, it squishes you up the wall a little bit.
Yeah, okay, yeah, I think that's, yes. Thank you for that. Thank you, David.
We have a question from Kenneth. Please go ahead.
Hi, David. Thanks for the talk. Very interesting. So I do have a question about, say, polariton interactions with each other, right? Do you think you might be able to see any effects of these interactions with each other, perhaps by an energy shift?
Yes. Yes, we do. And that's actually a big topic. I unfortunately cut out of this talk the data. So actually, if you go back to this type of data, and then first I removed the slide that showed a nice effect here. This ringing of this potential of the cloud here actually is renormalized by the blue shift. And there's two parts to that. There's the interaction with the excitons, which are sort of heavy and slow, and there's interaction with each other. And one of the nice things about these ringing experiments was that you could separate the contribution of the polariton from the contribution of the excitons, because the excitons have a different natural frequency, right? So the polaritons, the natural frequency is a function of both the polariton mass and the gravity. Now, somebody may be thinking, wait a minute, I thought a pendulum has a natural frequency that only depends on the radius and doesn't depend on the mass. That's true if your gravity is real gravity. This is not real gravity, right? This is fake gravity. Okay, so the mass is not giving the force of the gradient here. So we actually have a natural frequency that depends on the effective mass, and so we can actually separate out. And in this long PRB that Shavik did, you can very clearly separate out the part due to the polaritons repelling each other from the part of the polaritons being repelled by the excitons. Now, the strength of that interaction is still controversial, and it appears to be density dependent, and it appears to be dependent on a lot of different things. So there's renormalization effects, and so it's actually a very thorny issue to really work out those interactions. What you can say is in the high density limit, there's fairly good agreement of sort of a sort of density limited high density value for these interactions. At low density, there's a lot of debate still.
Right, thanks. That was, yeah, that was interesting.
Okay, any other questions? I also have a question. Could you explain again the mechanism of drag? So am I correct that, so you have non-condensate particles, but also you have a reservoir?
Yeah. Okay, so there's two things in the reservoir. There's excitons, which have a big heavy mass and do not respond to electric field. And then there's free carriers, free electrons and holes. This is actually doped, so it's all one side, it's mostly just free electrons. If I think probably the easiest way is start out forgetting about polaritons, just think about excitons. Okay, so I've got an electron hole pair, which I can think of like a little hydrogen atom. And now another electron comes in and bangs off of that, right? It's going to impart momentum to that exciton. Okay, now when we make a polariton, we're essentially saying that we have made the photon spend part of its time as an exciton. All right, and so it's a fractional, it has some fraction of it is an exciton, and that exciton part can interact with a electron. By the way, I didn't mention, it's kind of funny to think about. If you think about it purely as optics, we've got an experiment which we have a beam in and a beam out, right? And the angle of the beam out is being steered by a DC current, right? So it's actually optical beam steering with DC field, which is surprising. It's not a huge effect. It's 5 degrees or something like that, but it's a measurable effect.
Okay, where is important here that there is condensate? Because if one naively think of drag, you have condensate at rest, you have adjacent the second system, you induce flow, and condensate start to flow.
I would say in these experiments, the main importance of the condensate is just to make the drag visible, because it makes a very nice, sharply defined momentum, okay, which then can be shifted up and down by the electrons. Now, if it was an incoherent polariton gas, two things would happen. One is it wouldn't flow as far away. It would just kind of get stuck near where we created it, and also be much broader in momentum space, and it would be hard to see any contribution of the electric field. So there should be a drag effect on non-condensate particles as well, but it would be just harder to see. Now, just to be clear, in Ashton Bradley's theory, he was looking at a condensate with an interpenetrating thermal gas, of other particles. And in that case, it's actually a little bit of an artificial approximation to treat those as really separate populations, because in fact, the condensate is constantly exchanging particles with the thermal background. And so it's not really like you have two completely separate populations. In our case, the free electrons are really separate, like they are a completely separate population. So in some ways, his theory is actually more valid in our case than it is in the case that he was actually applying it to.
Okay, I see. Thank you. Do we have any other questions? Some time ago, I have read the paper. It's called Pseudo Drag by Kavokin and co-authors. you might familiar with it.
Sorry, what was it?
Some pseudo drag of condensate. It is done by Kavokin.
Yes,
It's
he had at least one paper. I think he was looking at what we were doing and trying to understand that. He was one of the people who didn't think that a condensate should directly have drag in the way that I described. And so he was coming up with an indirect way to get a drag effect.
due to the reservoir.
Yeah, but I think actually it's much more direct. I mean, you don't need to have his, I mean, I think his mechanism probably may also be true, but it's not necessary. You can have a direct effect of the electrons hitting the condensate.
Yeah, without coupling of condensate and the reservoir. Without this coupling.
Yeah, you don't, I mean, so there is an excitonic reservoir around, but I don't think that it matters for the effect we're seeing. It's actually what the exciton reservoir does is just the opposite. It's a source of friction. It's actually slowing the polaritons down, and so it's the non-moving exciton cloud is acting more like a pillow that just sits there and is a drag force on them.
Okay, thank you. Do we have any other questions? Please just go ahead.
Okay. Well, it's been very nice talking.
Fantastic talk.
All right. All right. Well, thank you. And we'll talk to you later then.
Nice evening.